In section 6.2, we're going to talk about orthogonal projections and orthogonal complements. Our starting point here is to define partner, say, of a subspace of Rn. So given a subspace V of Rn, we define its body, V perp, and the symbol here is the same as what we use to indicate that two vectors are orthogonal, but now we put it up on top, and it consists of all vectors that are orthogonal to every vector in the subspace V. So this guy V perp, or to read it out, the orthogonal complement of V, the set of vectors that are perpendicular to V, is a very important concept. So let's do a couple of examples. So let's fix a vector A in R2. So this is something we did earlier in the course. Now, if you take some vector A, then V in this case is span of the vector A. And then the orthogonal complement consists of the set of vectors that are orthogonal to, so now that is V perp. And the interesting thing here is that if we took some vector x, we could compute its projection onto V. So that guy there is the projection of x onto V. And then there's an analogous projection onto V perp. So this is the figure we've already seen. So we're going to try to generalize this. Maybe one more example before we generalize. So in R3, set V to be the set of all vectors whose third component is 0. So this is the x1, x2 plane. So let's see if we can draw this. This will be a little trickier. Let's see, so V is the xy, x2 plane. So that's V. We have x1, x2, x3. And now let's think about what is the orthogonal complement of V. So what's the set of all vectors? So vector y, so if you take a vector y and take its inner product with x1, x2, 0, and if this is to be 0 for all x1 and x2, then it must be the case that y takes the form like that, right? Its first two entries have to be 0. So the perp in this case is simply the x3 axis. Okay, so that is V perp. And again, what we're going to drive towards, we're going to do this formally, but just to give you an idea, is we're going to, so in this case, there's a natural way of defining the projection of the vector x onto the x1, x2 plane. So P of x, simply what you get if you zero out the third component. So this is called a projection. It has a very sort of clear, intuitive idea for this simple example, and now we're going to try to generalize this to a more general setting. All right, now I'm going to delete these examples, and then I will introduce an orthonormal basis for V. And then I'm going to define two vectors P and Q, one that lies in V and one that lies in V perp. So given any x in Rn, I define P as follows, and I define Q as whatever is left. So Q is equal to x minus P. Right, so what have I done? So the idea here is that if V is the linear space, so here we have V, and then we have its orthogonal complement. And given a vector x, P is something that lies in V. Right, so that's obvious, right? If you just look at this definition, it's obvious that this vector V, that the vector P lies in the space V because it's a linear combination of the UJs, and the UJs form a basis for V. And then Q lies in V transpose. For now, I'm just claiming this. That's something we'll need to prove. But this is the figure you should have in mind. So at least, so at this point, all we need to be completely on board with is the definition of P and Q. I'm given a vector space V, I'm given an orthonormal basis for that vector space, and then given any vector, I define these guys P and Q. Now let's write down a few different facts about P and Q. So first of all, x is equal to P plus Q. So this is obvious, right? Because that follows just right away from the definition of Q. So if I just move P over to the left, you get that x is equal to P plus Q. Then the second property is that vector P belongs to V. And this is obvious too, because if you just look at the definition of P, you see that it's a linear combination of the UJs. So that is definitely the case. Maybe we'll write this down. This is obvious. This is an obvious fact. Now, the third fact is a little bit less obvious, but the vector Q lies in the orthogonal complement of V. We need to prove that. And then the fourth fact, which we also need to prove, this is also not an obvious fact, is that Q, as it happens, the length of Q is the distance between x and the space V. So what do I mean by that? Well, this is simply the min over all vectors y in V x minus y. Okay, so let's prove this. So we'll start with 3. And I won't do it for a general vector in U right away. I'll start by doing it for the basis vectors. So fix a basis vector ui. And then I'll take the inner product between ui and q. So this is ui dot x minus ui dot p. So now I used the definition there, right? I just plugged that in to get this expression. And now next I will take the definition of p and I will plug that in, and that will give me and now the magic happens because this guy is 0 if I is not equal to j, and otherwise it equals ui squared. So this whole thing turns out to work out to x dot ui minus ui dot x. So this is 0. So q is orthogonal to every vector ui, and if x belongs to v, then x is some ci ui. So q dot x is some ci q dot ui, which is 0, because I proved that q is orthogonal to every basis vector ui. So that's that. So it occurs to me now that I'm actually being a little bit, I wouldn't need to do these weightings because I assume that the set is orthonormal, but I'll just leave them in. They're superfluous because I assume that the set, that all vectors are normalized, they all have length 1, but the formulas are certainly true anyway. And in fact, you can do this for an orthogonal set as well. So let's just leave that as it is. So having proved 3, we'll next prove 4. Let's erase. And then we'll do the proof of 4 in the same space. So let's pick a y in V. And then the distance between x and y, it's going to be convenient to square things. This is the same as the distance between x minus p plus p minus y squared. And now observe that this is equal to q, which we proved belonged to the perp, and this belongs to v. So what this means is that these guys are orthogonal. Let's write that as q. So this is equal to q squared plus p minus y squared, right? So this shows that x minus y, since this quantity is non-negative, I know that x minus y is bounded from below by q squared, which is precisely this statement. That's what I wanted to show, and I have now shown this. I've actually shown a little bit more, so as a bonus, we've shown that equality holds when y is equal to p. So in other words, there is a unique point. The point P is the unique point that is the distance norm Q to X. So it's precisely the one unique point in V that's the closest to X. So on the next slide, I'll just start by repeating a couple of definitions from the previous one. So the framing is the same as before. V is a subspace of Rn, it's a k-dimensional subspace, and I have an orthonormal basis Uj. Now what I'm going to do is define a matrix. Define the n by n matrix P as the sum, j goes from 1 to k, of uj transpose. So I think of uj as an n by 1 matrix. So think of these as column vectors, in other words. So then I form a square matrix. So, just to show you the shape here. So uj is the column vector, and uj transpose is a vector of that shape. So it's a sum of k outer products between very thin matrices. Okay, so this is my matrix P. Then Px is sum uj transpose times x, and that is just some okay, so this is the vector that I called p, lowercase p, on the previous slide. So it's just it's a convenient way of computing the vector p. Right, so remember on the previous slide, I included these normalization constants, which were completely unnecessary because I assumed that the basis is normalized, so that all these basis vectors have length 1. So, but just to make sure that you see that these are exactly the same expressions as I had on the previous slide. All right, let's get rid of those because I don't need them. Like so. Then, if I set Q to be the matrix that's identity minus P, then Q times the vector x is I minus matrix P times x is x minus matrix P times x is x minus vector P, which is the vector Q we defined on the previous slide. Okay, so these matrices P and Q are just the linear operators that map x onto the vector in V and the vector in the orthogonal complements. So P is this guy is what we call the projection of x onto V. And Q, likewise, is the projection of x onto the orthogonal complement of V. Now you can easily see that the range of P is equal to V, and this you can verify if you think it's fun. I'm not going to quiz you on these things, but I'll just tell you some fun properties of these matrices. So V is the range of P, and it's the kernel of the null space of Q. And now for V perp, it works exactly the opposite, like this. So remember, so the figure looks something like this. Given a vector x, you have px, or maybe I should use a different color. So px belongs to V. And do we have any colors left? Yes. Qx belongs to V perp. So the green is V perp, the blue is V. So the point is that I can write any x as Px plus Qx, where this guy belongs to V and this guy belongs to V perp. And these matrices, they have some other fun properties. So if I compute the square of P and apply it to X, well, this is P applied to Px. But now, since Px already belongs to V, it turns out that it doesn't make any difference. So this is equal to Px itself, and this works for every x. So P squared is equal to P. And this, in fact, is the mathematical definition of a projection. And what about Q squared? Well, Q squared is I minus P squared. Just do some matrix algebra. Maybe I should put quotation marks. To show them what I mean here is that there is a mathematical definition of what it means for a linear operator to be a projection. It's precisely that its square is equal to itself. So what do we get here? I multiply the terms together. I get 4 terms. Well, now P squared is equal to P. So this is just I minus P, which is Q. So Q squared is equal to Q as well. Right, so both P and Q are projections. They are what's called complementary projections. And now, so what if you're given a subspace? What if we are given a subspace V, but no ON basis? Then it turns out that you can still define projection. You can still define the perp, of course. Now you can also define the projection matrices. And there are many ways to go this, but one way is to build an orthonormal basis for V. So it turns out that there is a method that converts any basis for V to an ON basis. So, given a set of vectors Wj, there is this process that's called Gram-Schmidt, and that's the subject of in the next lecture, that gives you an ON basis. Okay, so that's what we'll do in the next lecture.